Okay, so let's have a look again. We've got a derivative there, got a quotient rule that we want to work out. Sorry, we want to work out a derivative for. So derivative of the top, e to the x, derivative, times the bottom, which is x squared minus 3, minus derivative of the bottom, which is 2x, times the top, over the bottom squared. And then, look, just a smidgen of tidying. Don't do it real right. Take e to the x out the front, and I'll get an x squared minus 2x minus 3. Not even fussed about trying to factorise that. It probably does, but let's just leave it as it is, hey? There's no extra marks. Find dividing x when x equal to 5. This time we've got a product rule. So the derivative of the first times the second plus derivative of the second times the first. And then we're just going to put x equal to 5. So I guess because it tied it up reasonably quickly, I just put natural log of x plus 5 over x. Put x equal to 5 in there, I get a natural log of 5. 5 plus 5 is 10 over 5, which is 2. So just rewrote the answer. So clear. Work out g of f of 3. So I thought instead of working out the function, if I just work out f of 3, I get negative 2. And then just substitute negative 2 into g. And I end up with positive 2. So I think that's a nice simple way of doing it. Find a rule for the function f of g of x in the form. So what have we got? We've got to put g of x. So I've got to put x squared minus 2 into f. So there's x squared minus 2, there's x squared minus 2. Just be careful with squaring this whole thing. I've left the negative sign out the front. X squared squared is x to the 4 minus 2 times a times b. So it's negative 4x squared. Negative 2 squared is positive 4. So it really is just a case of grouping all the terms together. Ax cubed plus bx squared minus c, or plus c. So we've got the right values there. A, b, and c are integers, so it's the format that we need. Evaluate, okay, again, anti-differentiate. The integral of e to the x is just e to the x. The integral of e to the minus x is minus e to the minus x, which gives me a plus in between. Put my 1 and 0, so I get e to the 1 plus e to the minus 1, subtract e to the 0 plus e to the 0. And so I end up with my e plus 1 on e minus 2. All right, so it's just paying attention to detail, something like that. My log laws, so let's just simplify the log expression on the left. So we're subtracting them, so we do a division within the log, t over t squared minus 4. So let's turn it into index form. So the power is 3 to the minus 1 equals t over t squared minus 4. I think the easiest way then really was just a bit of cross multiplying. The 3 multiplies the t, which I get the 3t, and then the t squared minus 1 multiplies the 1, gives me, sorry, the t squared minus 4 multiplies the 1 to give me t squared minus 4. And again, I've got now some nice little quadratic to factorise. So I get t equal to 4 or t equal to negative 1. I need to check both solutions, and we can see because log base 3 of t needs to be greater than 0. Only one of those solutions are valid, which is t equal to 4. What have we got? State the range of h. So normally, I guess my hyperbola would be in both sections, wouldn't it? But I'm just sketching for R positive. So I guess just in red there. All right, so we've got that section, yeah. So the range is obviously this value here at x equal to 0. I get 7 on 2 minus 3, which is a half. And I approach the asymptote at negative 3, so there's my negative 3 to a half inclusive. Find the inverse function, so swap the x and y values, so I get a plus 3. Reciprocate both sides, I think is probably a nice way. Multiply the 7 across, then subtract 2. Don't forget to rewrite as h inverse of x is equal to 7 over x plus 3 minus 2. Doesn't ask for a domain or a range or anything, so we can just leave it like that. A discrete random variable has probability mass function. show that k is equal to 12. So this one's a little bit different, isn't it? Because it's almost written like a continuous distribution, but it's only got specific values for x that are viable. So really what we're saying is, if that's x, x can be 1, 3, 4, or 6. And if x is equal to 1, I get k. If x is equal to 3, I get 3. Sorry, if x is equal to 3, I also get k from the second line. If x is equal to 4, I get 4k. I get 6k for 6. So the 12k has to equal 1, so it gets k is equal to 1/12. And there's the distribution down there. The expected value of x is x times p of x. So 1 times a 12th is a 12, 3 times a 12 is 3/12, 4 times 4/12, 16/12, 6 times 6/12 is 36 on 12. Add them up, I get 56 on 12. Divide both sides by 4, simplifies it a bit. And finally, the probability that x is greater than or equal to 3, given that x is greater than or equal to 2. So really, my conditional rule says that's the same as the probability of x is greater than 3 intersection greater than 2 over probability that x is greater than 2. The intersection for what set of values are greater than 3 and greater than 2, and that's where that comes from. Yeah, and then x is greater than 3 from the table. Greater than or equal to 3 is going to be 11 on 12. The probability that x is greater than 2 is also 11 on 12, so 1. You can see that it's between. All right, we've got some graphs. Sketch the graph of f and the graph of g on the axes provided. So what have we got in? Which one's which? G of x is equal to 3 sine x in red. So amplitude period, yeah. So the period for both functions is equal to 2 pi. So half a cycle gets done in pi, which means a quarter gets done in pi on 2, which is what I've got there. And all we can say, so at x is equal to pi on 2, we get y is equal to 3. And so that's in the red line. In the blue line, I've got 4 cos. So the amplitude is 4. Period is still 2 pi. So that's where we get our two graphs from. All right. Find the values of sine c and the value of cos c if f of c is equal to g of c. So solve the two equations equal to each other. So I get 4 on 3 is equal 4 on 3 is equal to sine c on cos c, which means tan of c is equal to 4/3. So if I just use my little right angle triangle, if that's the angle C, 4/3 is tan, opposite over adjacent, so 4 over 3. So it makes the other angle 5. And so now that gives sine C and cos C. From that, opposite over hypotenuse and adjacent over hypotenuse. What else do we do? Find the value of sine C, find the value of cos. So you can see back there, my point C. C is the x coordinate of the point of intersection, which is down there on the axes. I'm going to have to split my integral up, aren't we? That's the easiest way to do it. So from 0 to C and then from C, let A be the region enclosed by the horizontal axis of the graph F. On the axis, show the region A and the axis and also label the position of C on the horizontal axis. Calculate this area. Pi on 2, which I've got here. It's from 0 to C and then from C to pi on 2. So if we do all that, I get things in terms of cos C and sine C, and sine C and cos C in the previous question. So if we're just a little bit careful there, cos of C was 3/5, sine of C was 4/5. So if we're just careful with substituting those points in, we should come out with a nice value of 2. All right. What have we got? P hat, random variable represents a sample proportion of customers who bring their own shopping bags. From a sample consisting of all customers, 95% confidence interval. P hat was used with the approximate. Okay, so if that's my interval, so don't forget that that's my interval. So if you like, P minus 1.96 sigma, P plus 1.96 sigma is equal to those values. So P hat is the average of those two values. So that's just equal to 1/10, which is 5,000 over 50,000. So that's in the center. And we've been told to use 1.96 as being equal to 49 on 25. Find the end value. So we know that the standard deviation is given by the square root of P hat minus times 1 minus P hat on n. So substitute some values in. P hat is 1/10. The sigma, 1.96 is 49 on 25. P times 1 minus P over n is down here, 1/10 times 9/10 over n. So what does that give me? So that gives me 9 on 100 over n times 49 on 25. So if you like, I've got 49 on 25 times the square root of 9 over 100 n, yeah? And the square root of 9, which is equal to 49 on 25 times the square root of 9, which is 3 over 10. Oh, it's up there. Sorry, I didn't see it up here, which is where those values come from at the top. Yeah, so the square root of 9 is 3, the square root of 100 is 10 root n, and that's equal to the difference. Yeah, so that's the mean in the middle, 5,000 on 50,000, which is the 1/10. Yeah, so that difference is 147 on 50,000, which is that value out there. That's where that comes from. So what does that mean? So it means then you can sort of see straight away 349 is a 147, we got a 147, so the square root of n is equal to 200. So n has to equal 40,000. All right, it's just getting used to the terminology really with that sampling proportion. What have we got here? Diagram, whole heap of points, 0, 0, 0, 2, 3, 2, which is up there. B, 0 down here, that's fair enough. On the same axis as the trapezium, part of the graph of a cubic polynomial function is drawn. It is a rule y equals ax minus b squared, blah, blah. At the local maximum, I can find it in terms of a and b. At the local maximum of the graph y equals b. So at the maximum here, y is equal to b. So where does my maximum occur? It's when the derivative is 0. So I'm going to use a chain rule, a product rule. So I've got the derivative of the first, actually I'll do that. I've got the derivative of the first, which is a, times the second, plus, which is that, plus the derivative of the second, which is all of this, times the first, which is ax. Now, because I'm going to be looking for where this is equal to 0, I'm going to keep anything I can out as a common factor. So the a and the x minus b, I'm going to take them out as common factors, which leaves me with an x minus b here from the first term and a 2x from the second term. So there's my derivative, which means my solutions are at x equal to b and x equal to b on 3. And x equal to b matches off with the graph, doesn't it? So x equal to b on 3, if you come up, is that point there. So if we substitute f of b on 3 into my equation, I get ab on 3 times b on 3 minus b all squared. So b on 3 minus b is 4b squared on 9 because I've squared it. So we get b, which is the y value from in here, is equal to 4ab cubed on 27. So rearrange a little bit and we'll get a is equal to 27 on 4b squared. All right, so it's just sort of keeping question 27, keeping things in place. The area between the graph of the function and the x-axis is removed from the trapezium as shown. So show that the expression for the area of the shaded region, so I'm going to work out the unshaded areas. So area 1, you can see there. Expand that bracket, x squared minus 2bx plus b squared, and then multiply by ax. I'll put the a out the front, multiply by x. So I've got that dx, integrate between b and 0. So don't forget the x is the pronumeral we're integrating with respect to. So add 1 to the power and divide, add 1 to the power and divide, etc., etc. So we end up with a sort of messy looking expression. The triangle, area 2 is just a half the base times the height, which comes out to be 3 minus b. So what does this expression become? 32. Oh, it's 3b to the 4. Jeez. So that just ends up being ab to the 4, isn't it? That's ab to the 4 on 12 plus 3 minus b. So that's the area of the unshaded region. So I'm just going to, what am I going to do there? I'm going to substitute my a value in. So a was equal to, from the previous, 4b squared. 4b squared. So if I substitute that in, there's my 27 on 4b squared times b to the 4 on 12. We get a few things cancelled out. 4 goes into 12 goes into 27. 3 is a common factor. B squared into b to the 4. So I get 9b squared on 16 plus 3 minus b. That's the whole unshaded region. The rectangle, so in the shaded region will be 2 by 3, which is the rectangle that you would get. Subtract that unshaded region. So 6 minus all of that will give me that expression there. All right. So look, I think doable. Just have it set out nice and cleanly, nice and clearly. Example, area is equal to b plus. Find the value of b for which the area of the shaded region is a maximum. And find this maximum area. So there's the area there, isn't it? From the 3 minus 9b squared on 16, how do we find a maximum? We do a derivative. So if we do our derivative, we'll get b is equal to 8 on 9. So if b is equal to 8 on 9, we're going to get a maximum area. And if we put that 8 on 9 into the rule for the area, and just do a little bit of hocus pocus and get some like terms together. What are 9 15, 16s, 9 16s are 144, so there's our common denominator, although 16 goes into both of them. So, you know, it's just a case of trying to tidy things up, all right? Yeah.